It is the last week of August, 1940. The North Atlantic is dark and cold and full of death. A gray-hulled ocean liner moves through the water without lights, no running lamps, no cabin glow, nothing that a periscope might fix on from 300 yards away. It zigzags. It does not run straight because a straight course is a predictable course, and a predictable ship is a dead ship. The vessel is the Duchess of Richmond, a Canadian Pacific liner requisitioned as a troop ship and painted the flat gray of wartime. More than 1,000 Royal Navy sailors crowd her lower decks, bound for Halifax to collect 50 antiquated American destroyers, hand-me-down warships given up by America in exchange for Caribbean naval bases. Britain has agreed to trade away strategic territory for aging ships. It is not a good deal. It is the only deal available. On board is a Welsh physicist named E.G. Bowen. He is not a sailor, not a soldier, not a diplomat. He is 30 years old, and he is carrying a small metal deed box, the kind a solicitor uses for property documents. It is locked. It does not look important. Nothing about it announces what it contains. The box is designed to sink. If a German torpedo finds this ship and the box cannot be saved, it is built to go to the bottom before anyone can open it. Britain has looked at everything in that box and decided the enemy must never have it, even at the cost of losing it entirely. What is in that box, and what kind of war produces a country that builds a self-destruct mechanism into a case of documents? That is the story of the Tizard Mission. It begins in the rubble of occupied Europe and ends in an American hotel room. What it cost Britain to fill that box, and what happened to the world because the box reached the other shore, is a reckoning that took decades to come fully into view. Summer, 1940. The picture in Europe is close to catastrophic. France has surrendered. The Low Countries are occupied. Norway is gone. In the skies above southern England, Royal Air Force Fighter Command is fighting the Luftwaffe day by day, sector by sector, with margins that leave no room for error. The Blitz is beginning. German bombs are falling on British cities. British factories, the ones still standing, are running at absolute capacity producing fighter aircraft, because fighters are the only thing between Britain and the end. Britain is the last country in Europe not under Nazi control, and it is running out of room to maneuver. Here is the paradox that makes the story possible. In laboratories and universities across Britain, scientists have spent the previous years developing military technologies that could fundamentally change the shape of the war. Technologies Germany does not have. Technologies America has not imagined. The ideas exist. The prototypes exist. The expertise exists. And Britain cannot use any of it, because British industry has no remaining capacity, and British factories have bombing raids to survive before the morning comes. Into this situation steps a 55-year-old chemist named Sir Henry Tizard. Trim, bespectacled, upright, a man with the composed bearing of a schoolmaster, and a mind that cuts precisely through what other men make complicated. He had learned to fly during the First World War, had developed the octane rating system for aviation fuel, had spent the 1930s as one of the chief architects of Britain's radar defense program. He is, in the summer of 1940, one of the most consequential scientists in the country. He is also, at this particular moment, politically bruised. His adversary is Frederick Lindemann, once his closest friend, now the scientific advisor to Winston Churchill himself. These two men had met as young scholars in Berlin. They had returned to Oxford as colleagues. Something had soured between them. Professional competition, accumulated friction. Two brilliant men who had come to see the world very differently. By 1940, the friendship is long dead, replaced by a rivalry that has teeth. Lindemann's position is Churchill's position, and Churchill is Prime Minister. When Tizard argues for sharing Britain's most advanced secrets with America, going to Washington with everything, trading scientific transparency for industrial partnership, Lindemann opposes it. Why surrender Britain's most powerful advantages to a country that is still officially neutral? A country that has not committed to fight and may never do so? Churchill takes some convincing. The fall of France and the evacuation from Dunkirk have clarified certain realities, and eventually the authorization comes. But it comes without enthusiasm. And it comes while Tizard is already carrying the weight of having just lost a major scientific argument with the Prime Minister on a different matter entirely. He is heading to Washington diminished. He is heading to Washington anyway. Tizard's calculation is this: take Britain's secrets to America, lay them on the table, and exchange them not for money or military commitment, but for the one thing Britain cannot manufacture: industrial scale. America has the factories, the resources, the institutional infrastructure to take a laboratory prototype and produce it by the millions. Britain made things by hand in 1940. America could make things by the train car load. What Tizard is bringing to that table begins here. February 21st, 1940. A physics laboratory at the University of Birmingham. Two men, John Randall and Harry Boot, are preparing to test a device they have been building since September under the guidance of their department head, Mark Oliphant. The problem they are trying to solve determines everything that follows. Radar works by sending out a pulse of radio energy and listening for the echo when it bounces back from an object. The shorter the wavelength of that pulse, the more precisely the radar can resolve what it has found. The difference between seeing a smudge on a screen and seeing the outline of an aircraft. In 1940, effective airborne radar requires a wavelength of roughly 10 centimeters. The equipment that generates 10-centimeter signals at useful power levels fills a room. No aircraft can carry it. The technology that could win the war in the air and on the Atlantic cannot be installed in anything that flies. Randall and Boot have spent months on a new kind of magnetron, a device that generates microwave energy using a very specific geometry of resonant cavities inside a copper cylinder. The cross-section looks, as it happens, like the chambers of a revolver. Their design builds on theoretical groundwork laid by a Dutch engineer named Klaas Posthumus, refined through months of calculation. On February 21st, they run the test. The instruments return a reading, over 400 watts, at 9.8 centimeters. They check again. The number does not change. These are careful men who trust their instruments, and their instruments are telling them something that breaks every existing understanding of what microwave power generation can do. A room-sized device produces perhaps a tenth of this output. Randall and Boot are looking at a device that fits on a workbench. Within a week, with minor modifications, the output climbs to 1 kilowatt, within months to 10, then 25. The experimenters can hardly believe it is microwave power at all. The workbench has done what the room could not. The British Admiralty moves quickly. By April, a contract goes to the General Electric Company at Wembley, outside London. GEC's engineers, led by Eric Megaw, take the Birmingham prototype and make it manufacturable, sealing the vacuum, adapting it for field use. In August 1940, Wembley produces 12 prototype cavity magnetrons. Number 12 is designated E1189. It has 8 internal cavities, rather than the 6 shown on the drawings. No time to amend the plans, so the factory floor makes a decision and moves on. It is smaller than a grapefruit. Cold, heavy for its dimensions. Machined to very fine tolerances. And it can produce 10 kilowatts of pulsed power at 10 centimeters. Enough resolution, enough range to detect the periscope of a surfaced submarine at night from an aircraft flying in complete darkness. Number 12 is placed in Bowen's hands. Bowen is told to take it to America. The night before the mission departs, the magnetron spends the night under Bowen's hotel bed in London. In the morning, the deed box, magnetron inside alongside its documents, is strapped to the roof of a taxi bound for Euston Station. At Euston, an eager porter seizes the case before Bowen can stop him and sets off into the crowd. For a moment, the most valuable piece of hardware in Britain is somewhere in the middle of a busy London railway station, being carried by a man who has no idea what he is holding. Bowen retrieves it. The moment passes. In Liverpool, by contrast, the magnetron receives a full army escort to the ship. That is the Tizard Mission in miniature. A night under a hotel bed, a near disaster at a railway station, and then, belatedly, a squad of soldiers. Urgency and improvisation in collision with the weight of what is actually at stake. The box Bowen carries onto the Duchess of Richmond contains more than the magnetron. There are technical drawings for the Whittle jet engine, Britain's nascent program for gas turbine propulsion, which has no equivalent anywhere in the world. There is a briefing document on the Frisch-Piles memorandum, the theoretical framework suggesting that an atomic explosive device is not merely possible but buildable, given sufficient quantities of separated uranium-235. There are the technical details of Chain Home, Britain's coastal radar network. There is the G hyperbolic navigation system. One-of-a-kind documents, most of them. No copying machines, no backups. What is in that box exists in that box. And if the box goes to the bottom of the Atlantic, it goes with everything in it. The Duchess of Richmond sails on August 29th. The Battle of Britain is still being fought in the skies overhead. In the Atlantic, German U-boat commanders are in what they will later call their happy time. Allied ships going down faster than they can be replaced. Wolf packs working the convoy routes with brutal efficiency. The ship zigzags. No lights. 1,000 Royal Navy sailors below decks, on their way to collect 50 obsolete American destroyers. And somewhere above them, a metal deed box designed to sink. The Duchess of Richmond arrives in Halifax on September the 6th. The box arrives with it. Washington, D.C., September 19th, 1940. The Wardman Park Hotel, a grand Edwardian building north of DuPont Circle, its meeting rooms wood-paneled and formal. The end of a humid summer, suited men around a table, ashtrays, coffee going cold. The British and American delegations face each other with the careful politeness of people who are not yet sure how much to trust one another. The Americans are represented by the National Defense Research Committee's Microwave Committee, chaired by Alfred Loomis, a Wall Street millionaire who has converted his private estate at Tuxedo Park into a physics laboratory equipped to rival a university. Vannevar Bush, Roosevelt's science czar, is in the background. These are serious men taking a serious meeting. The British open with Chain Home. Tizard's delegation presents the technical specifications of Britain's coastal radar network, the system that has been giving Fighter Command early warning of Luftwaffe approaches since before the Battle of Britain began. The British expect this to impress. It doesn't. The Americans have their own long-wave radar, the Navy's CXAM system. It is not identical to Chain Home, but it is close enough that the British specifications produce no revelation. The room does not lean forward. Britain's opening card has landed flat, and the pressure is now entirely on whatever comes next. The Americans, for their part, show what they have in short-wavelength radar, and then they admit the problem. Their Klystron transmitters produce 10 watts. They are at a dead end. Short-wavelength radar has the precision they need, but nothing they have built can generate enough power to make it useful. They have the right idea and the wrong equipment, and they know it. The room sits with that for a moment. Then Bowen reaches into the box. He produces a copper cylinder, small enough to hold in one hand. He sets it on the table and explains, with what his own memoir would later characterize as a flourish, that it produces 1,000 times what their best transmitter can manage. 10 kilowatts of pulsed power at 10 centimeters. Not a theoretical projection, a working device, the one in front of them. The American engineers are stunned, not politely interested, stunned. These are the best microwave scientists in the country, men who have spent years working at the outer limit of what the technology can do, and a Welshman in a suit has just moved that limit by a factor of 1,000. The word stunned appears in multiple independent accounts of that meeting. Bowen and John Cockcroft, who sits alongside him, quiet and precise, one of Britain's foremost nuclear physicists, lay out the full specifications. The resolution. The range, what it can see in the dark, in all weather, at altitude, from a moving aircraft. The tension that had characterized the opening dissolves entirely. What remains is something closer to disbelief, working its way toward understanding. Later that same week, Tizard and Cockcroft travel to Columbia University. They meet Enrico Fermi, one of the finest physicists alive, a man who has spent years probing nuclear chain reactions. Tizard's delegation briefs Fermi on the Frisch piles concept, the theoretical case for a uranium explosive device, its feasibility, the mathematics behind it. Fermi listens. He is skeptical. His research is oriented toward power generation, the controlled, peaceful application of nuclear energy. The idea of an operational bomb strikes him as unlikely. He says so. The meeting ends without consequence, or so everyone present believes. Over the weekend of September the 28th, the delegation reconvenes at Loomis's estate at Tuxedo Park, an hour north of the city. Autumn is coming on. The trees are beginning to turn. In a glass-walled laboratory that sits incongruously against the Victorian stone of the main house, Bowen demonstrates the magnetron again. Drawings, construction details, everything. The plans for what will become the MIT Radiation Laboratory begin to take shape. American institutional will and British scientific invention finding their common purpose over a workbench in upstate New York. Britain gave America something it had made 12 of. America gave it back as $1 million. The Bell Telephone Company receives the first commission in October 1940 and produces 30 working copies that month. By the end of the war, more than 1 million cavity magnetrons have been manufactured in the United States. The MIT Radiation Laboratory, founded at the end of 1940 with an initial budget of $455,000, approved by Vannevar Bush, employs over 4,000 people at its peak. It produces the microwave radar that guides Allied bombers through cloud cover, locates German submarines in the dark Atlantic, guides paratroopers to their D-Day drop zones, and brings down V-1 buzz bombs over England in 1944. Britain handed over a handmade prototype. America returned an industrial revolution. There is a footnote here that illuminates how history actually works. When Bell Telephone's director receives magnetron number 12 and X-rays it, he finds 8 cavities inside. The GEC drawings specify 6. A transatlantic cable goes to Birmingham. McGow's response? There was no time to amend the drawings. He had asked for 12 units, 10 with 6 cavities, 1 with 7, 1 with 8. Number 12 was the one with 8. America had the drawing and the sample and chose to copy the sample. Early British magnetrons had 6 cavities. American ones had 8. A rushed factory floor decision on an August morning in 1940 permanently shaped the architecture of American radar. Sometime in 1942, a German U-boat commander surfaces his vessel at night. He has done this many times before. The dark has always been his protection, a surface charge of the batteries before the next dive. He cannot understand why Allied aircraft keep finding him. He cannot understand what has changed. His submarine service will lose hundreds of boats before the war ends, and the commanders who survive will have no satisfactory explanation for what found them in the dark. The copper cylinder in the hotel room. That is the answer they never receive. The Battle of the Atlantic, which Germany came close to winning in 1942, turns. Not on a single day, not through a single device, but through the gradual, cumulative advantage of seeing further, more precisely, in all conditions, from the air. The convoys get through. The food and fuel and ammunition Britain needs to survive continue to arrive. The margin is never comfortable, but it is enough. Then the deeper irony. Britain told Enrico Fermi about the bomb. Fermi didn't believe it. On December 2nd, 1942, in a converted squash court beneath the stands of Stagg Field at the University of Chicago, Fermi achieved the world's first self-sustaining nuclear chain reaction. The seed Britain planted in that Columbia University office, dismissed in a polite afternoon of professional skepticism, had germinated into something neither side had fully believed possible in September 1940. The Tizard Mission touched the Manhattan Project before the Manhattan Project had a name. Britain handed the conceptual key to the most consequential weapon in human history to the man who would prove it worked. He told them, calmly and professionally, that he doubted it would. He was wrong. There is one more thing to reckon with. When Tizard raised the matter of the Norden bomb site, America's prized precision bombing technology, one of its most closely guarded military secrets, Roosevelt declined. He was apologetic. He explained that the Norden was unavailable unless it could be demonstrated that Germany had something comparable. Tizard was, by his own account, not unduly dismayed. He believed there were other American technologies of more practical value. His equanimity was real. So was the asymmetry it sat beside. Britain had attached no conditions to anything it gave. America, facing the same table, drew a line. It was a reasonable line. It was also an instructive one. The war turns. It turns slowly, at enormous cost, and at no single moment. But the technologies that Britain gave away in a Wardman Park hotel room in September 1940 are present at almost every turning point. The radars in the night fighters, the navigation systems in the bombers, the centimetric equipment that finds submarines in the dark, the conceptual seed that becomes, 3 years on, the first nuclear chain reaction beneath a university sports facility in Chicago. None of it wears a name tag. None of it announces its origins. It simply works. Taffy Bowen stays in America. He works as a liaison with the radiation laboratory, shepherds the cooperation the mission has set in motion, and remains. He never comes home. 47 years later, he writes his memoir and calls it Radar Days, the quiet title of a man accounting for what he did with the best years of his life and where he spent them. John Cockcroft returns to Britain, rises through the scientific establishment, leads the Canadian Atomic Energy Project, and in 1951 is awarded the Nobel Prize in Physics for his work on particle acceleration. One of the most decorated scientists ever to carry a piece of hardware across a U-boat ocean in a metal deed box. Henry Tizard returns to public service. He serves as Chief Scientific Advisor to the Ministry of Defense, chairs committees, receives honors. He dies in October 1959 at 74. His role in what may have been the single most consequential scientific exchange of the 20th century is, by then, already receding from public memory. He gave away Britain's greatest secrets in a calculated act of desperation dressed as generosity. The inventions endured. The man who surrendered them did not. Lindemann watched the alliance prove decisive. He watched the Americans arrive, and he watched them arrive with the magnetron Britain had sent them, scaled up and installed in aircraft that found his country's enemies in the dark. He had opposed the mission. The war answered him, and the magnetron itself did not retire when the war ended. A device that Britain built 12 of, guarded under a hotel bed in London, nearly lost to a railway porter at Euston Station, carried across an ocean full of submarines in a box designed to sink, became, after 1947, the key component of the commercial microwave oven. It entered millions of kitchens. It reheats dinners. It heats coffee that has gone cold. Britain received no royalties, no commercial benefit of any kind. No conditions had ever been attached. The gift was, in every sense, total. James Finney Baxter III was a Pulitzer Prize-winning historian who served as the official chronicler of American wartime science. Writing in 1946, while the conflict was still fresh and its full dimensions only beginning to be understood, he set down a verdict on the moment Bowen placed the magnetron on that table. When the members of the Tizard Mission brought it to America in 1940, they carried the most valuable cargo ever brought to our shores. He was right. That is not in question. The question the story leaves behind is a simpler one. Most valuable to whom?